In this video, we'll review how processes work. On a regular general-purpose computer, you wouldn't want the whole computer to crash just because you ran a bad program. It's okay if the program crashes, but the computer should keep running. That facility has been around for quite a while now. Usually it's implemented in the form of a process separation. Process separation. The hardware provides some small facilities that the operating system then uses to create this isolation, little padded room where you can run a process that you don't really trust to do the right thing. And if it does the wrong thing, the process will be killed by the operating system, but the machine itself won't be affected. Primarily, this is implemented through what's called virtual memory hardware. This allows the operating system to say what parts of the memory are accessible to a given user, and then there are some instructions that are privileged, that are only the kernel may execute. You don't need much more than that to create the process abstraction. Right. So a process then may only execute non-privileged instructions. Basically, that means it can read and write from memory. It can compute things like division and shifting bits in registers, that sort of thing. It cannot access the memory of other processes due to the page tables. It cannot change its own page table. It can't talk to peripherals. Can't do almost anything except access its own memory and compute stuff. To do anything else, it needs to issue system calls. A system call is implemented through an assembly instruction, and basically it switches to supervisor mode, which is how the kernel executes, and then starts running at a known instruction. I guess an important thing to note is that on any given core at any given time, you're either running the process, or you're running the kernel. They're not running at the same time. You're only running one process too at any given time. They switch quickly, and sometimes you don't. I mean, it's hard to notice, of course, the difference. But they're actually sharing the CPU over time. For a few milliseconds, one process is running and then another is running, and sometimes it's much less than milliseconds too. Right. Virtual memory is basically a big lookup table for any access to memory. And this goes for both in user space where you're running a process and in the kernel. Every access is mediated by this lookup table called a page table. In the page table, it's basically a long list saying for any 4 kilobyte chunk of the 64-bit virtual address space, what does it correspond to? It can correspond to nothing, which means if you try to access it, it'll result in a page fault. That's an interrupt, which starts running the kernel. The kernel can then decide that, well, that was okay. There was supposed to be something there. Let me fix it and then return. And then the process continues running seamlessly. Or the OS might decide, the kernel might decide that that was an illegal access, in which case the process will receive a segmentation fault error and be stopped immediately. Right. So this page table, it maps for 4 kilobyte chunks. It might point at a 4 kilobyte chunk of physical memory, anywhere in memory really, including other processes' memory. That's how you share memory between processes. It might point at nothing. Or there's sort of a third case. This one is not an accurate illustration. There's never a pointer to disk. Disk doesn't have address space in that sense. But there's a third case where the kernel had intended to put an entry in the virtual memory in the page table, but it didn't get around to it yet. So now if you try to access that, you'll get a page fault. You'll switch to the kernel. The kernel will see, okay, that page, well, yes, I had intended to put 4 kilobytes of free memory there, or I had intended to put the contents of this file over there, so on. So in that case, it'll do it and then return. And that's sort of an important concept, I suppose. So important difference between the memory already being mapped into the page table, because then accesses are very fast, or not being mapped in which case you get a page fault, which takes time to process, and that can be quite slow. It depends on where it's going to get the contents from. Right. And if it's unoccupied, properly unoccupied, then you're always going to get a segmentation fault. There's a difference. Page fault is just an interrupt to the kernel, and the kernel will decide what to do. A segmentation fault is a signal from the kernel to the process saying you did something illegal. Okay, so it's important to note here that virtual memory is always in between, like you issue a move instruction. Everything goes through the virtual page table, the page table, the virtual memory. So anytime you do a move, you first have to look up in this table, well, where is that in actual memory, actual physical memory? Of course, the process doesn't do that. The CPU does it for you, but it still needs to do that lookup, and that's not free. If you have a large address space and you're using places all over, well, using memory all over the place in that address space, this will actually slow things down significantly for you. If you have lots of locality, if your accesses are within one page for a while and then within another page for a while, or within a set of 100 pages for a while, then usually it'll be fine, because there's a cache called the translation look-aside buffer, which remembers the pages you've looked up recently. And it's extremely fast. So there I think there's maybe a 1 cycle cost to do the lookup. If your access, or if the page you're accessing is not currently in the TLB, then it's a RAM lookup. Potentially, it could be elsewhere in the cache hierarchy, but it could be as much as a few hundred cycles, just to see what address was I supposed to read. So you end up getting potentially a substantially increased cost for your move. That said, everyone uses virtual memory. I would never recommend going to physical memory unless you have some very special circumstances. And you also can't do that in the process. You'd have to do it in supervisor mode, writing kernel code, and it sounds like a bad idea. So don't go there. All right, so to switch between processes, the OS will have to switch the page table. There's a special register. It's called CR3, not important. You move a pointer to that register. Now suddenly you're using a different page table. This is naturally a privileged instruction, so only the kernel can do that. But that's sort of how we switch processes, or a large part of it. I think an important thing to note there is that if you switch processes, if you change the page table, you do have to clear the TLB. So anytime you come back, you're going to have an empty TLB, and your accesses will be slower for a while until you've populated the cache again. Right. So how do we get this process isolation? I mentioned it a little bit. Let's see some more detail. So in the page table, there's for every page, there's a little bit that says, is this user accessible? If it's user accessible, then the process may perform moves to or from that memory. If it's only supervisor accessible, then any access will result in a page fault, and the kernel will have to decide what to do about it, and usually it'll be a segmentation fault. That's if you're in user mode, you're running a process. If you're in supervisor mode, you can do anything you want. That is, you can't necessarily access all memory. If you want to access memory, it needs to be mapped into your page table first. But of course, you have the permissions to modify the page table, so you can do that and then access the memory. Because it's so powerful, it's very easy for the kernel to crash the entire machine, do one bad thing, a null pointer dereference, let's say. There's no such thing as a segmentation fault for the kernel, just, saving everything. In that case, you're done. You have to reboot the machine. And that's a good case. In a bad case, you have some malicious actor now taking over your machine. So we must ensure that we only ever run trusted code in the way intended if we're going to run in supervisor mode. So how do we ensure that? Well, I guess there's a few steps to it. First, there's the transition between user mode and supervisor mode. It'd be very important that when you're in user mode, you can't just switch to super user mode willy-nilly. There are two ways to go from user mode to supervisor mode. You can issue a system call, and that's sort of synchronously in the program flow. You say, okay, now make the right system call, let's say. So that transitions from user mode to supervisor mode, starts running at a known instruction in the kernel on a separate stack. So now the user program doesn't really get to impact the program flow there. The only thing you can do is pass some parameters, and the kernel will be very careful inspecting those parameters to make sure they're safe before doing anything. Alternatively, there might be an interrupt. Either you do something you're not supposed to, or a peripheral like a timer or a disk drive or a network interface, something like this, issues an interrupt voltage on a pin on the CPU really. And the CPU will stop what it's doing, stop running the user stuff, immediately switch to supervisor mode, start running at a known start instruction with a separate stack. So again, the user is no longer running. It doesn't have any control over what the kernel will do, other than perhaps some parameters set somewhere. And those parameters will be carefully checked before we do anything. And then there's the switch back. How do we get from supervisor mode to user mode? There's basically only the one. There's one instruction, iret, which switches back to user mode. Before we do that in the kernel, we have to make sure we restore all the register contents to what they used to be before the system call or the interrupt happened. We switch to that includes switching to the original stack. And then with iret, it takes I think it takes the instruction pointer off the stack. Could be wrong. And returns it, and returns control to the user process at the instruction pointer that was on the stack. So now from the process's point of view, execution continues seamlessly, whether it happened from a system call or an interrupt. But you see here how a system call is extremely different from a function call. Sometimes people will kind of conflate the two. There might be sort of system functions that are part of libc that feels like, oh yeah, that's a call to a system function, so that's got to be a system call. It's not the same thing at all. There are function calls to various functions that are all in user mode. And then there are system calls that transition to supervisor mode. That's a much bigger deal. And much more expensive, I might add. Okay, how is a process made? There's initially, well, first when the computer starts running, it's only running the kernel. somewhat simplified. At some point, the kernel creates the first process. It's a very specialized case. It's called init, has ID 1. That's the only process ever created this way. All other processes are created by forking an existing process. So init will fork itself. Now there's 2 inits. And then it'll issue an exec system call, which replaces replaces a process. The entirety of the process. It replaces the code and all the variables. The whole page table is replaced. Original process completely disappears, except for the file descriptors, which remain. So a simple example, if we're running this command on the command line. Here is a command prompt, right? And it says, we say echo hello. So we're running bash, we say echo hello. That's supposed to run the program echo with the parameter hello. Now bash reads the command from standard in, decides to fork. So now there are 2 bashes running, or SHs here. 2 bashes. The child, the newly created one, then calls exec, replacing itself with the echo binary. Only standard out, really, in this case, only standard out is of any interest. That remains. It's the same standard out, so that when echo writes something to standard out, it shows up on the terminal that we were using. Finally, the parent, generally speaking, waits for the child to finish executing and then prints out the command prompt again. A single thread may contain a single process may contain multiple threads. Why do we have threads? The main reason to use many threads is so that you can use more than one core. It's not possible to use more than one core, or even hardware thread or hyper thread, as it's sometimes referred to, without having multiple kernel threads, really. So that's the main reason. Of course, it might also be that you want to do many things concurrently, but you want to program in a sequential fashion. Then it's also convenient to run many threads, maybe each performing one task, and they all share a smaller number of CPUs. That's also fine. The threads within a process all share the same page table. They have the same address space, the same file descriptors. This is very convenient. They can all work on one task together. Like all these cores working on one job seamlessly, more or less. But it's also very dangerous because you could end up with inconsistent results. If you're accessing shared memory from one thread within the process, you might put the data structure temporarily in an inconsistent state. Let's say you have deallocated some memory, but not yet changed the pointer that used to point at it. You're going to do that next, of course, but before you do that, another thread might dereference the pointer. One example. So this needs to be very carefully managed. If you're going to work with shared memory, it's important to very carefully manage these so-called race conditions. We'll get to that in lots of detail later on. Of course, you've seen this before. We'll look at the performance aspects of it. Okay, so finally, some basic process manipulation, and we'll be using this for homework 1 as well as for any in-class exercises. To see the list of processes, it's PS. If you do PSXA, it'll show you all processes on the system as opposed to just the ones that belong to you, and the U there shows what user it belongs to as well. Top or HTOP just lists the most CPU hungry processes. That can be handy sometimes. Keep in mind though that it'll list all of them, and we have one shared machine for lots of us. It can get a little confusing. Kill will send a signal to a process. Signals is not something we'll go into in detail later, but in detail at all in this class. 361 covers it in some detail. But it can be handy if a process goes kind of awry. If you lose terminal access to it, you can't control C it, you can always send a kill signal to it and shut it down. If it's refusing, a process can refuse some signals, send a kill -9, and then it'll die for sure. Time, very good. You say time and then process, or your program you want to run, it'll just measure how long it took. ltrace lists over time. It monitors all the dynamically loaded library functions that you execute. It cannot tell that you execute library functions from a static library. And then strace monitors system calls. Oftentimes there will be, so for printf, for example, you'll catch printf on ltrace, and then you'll catch with strace a write system call. That's the one that the printf uses to actually access the screen or the file descriptor. perfstat collects aggregate statistics. So usually you would say perfstat in the program you want to run, and then it'll say how long it took at the end. There's other ways you can collect aggregates too over a shorter period of time, attached to a running process, that sort of thing. But it's always aggregates. It has a convenient list of things that it collects normally. If you run perf list, you can see all the other stuff that it can collect, and there's really a lot, and we'll use some of that in lots of detail later. Finally, perf record will periodically check and record primarily the instruction pointer. So every now and then it'll stop the program and see, oh, what was the instruction pointer? Just keep doing that. And then when you're done, you can run perf report and get a statistical view of what the instruction pointer was at all these different times. If you get enough samples like that, you can get a pretty accurate profile of what the program spends time doing. There's lots of various ways of using perf record and report, and we'll play with that a lot later. Very powerful tools. For now, without any special parameters, perf record will record periodically in terms of CPU cycles, every 3,500 CPU cycles or something like that. And perf report will just show aggregates across everything. Okay, that's all we've got for today, and I'll see you on Friday. On Friday we're going to have a mock exam, and the mock exam will probably require use of some of this, as well as SSH to pages. If you haven't yet figured out your SSH access to pages, got it working with passwordless login and convenient configuration, that sort of thing, do it now so that you don't struggle with that during the short time of the exam. All right, I'll see you Friday.